Hello everyone, welcome to our new session of fluid mechanics. Today we are going to start our new session that is the based on Darcy-Weber equation which shows us the loss of head due to the friction in a pipe. So if you talk about our previous session, in that session we had already covered about the loss of head or the drop of pressure due to head in the pipe or in the plates that we had covered in a previous session. So in this session we will see about the most important topic of this unit, that is the Darcy-Weber equation. Okay, so the another name of this derivation, that is the loss of head due to the friction in a pipe. So this derivation is also known as Darcy-Weber equation. So most IMP topic of this session. So let us start this unit of this session. Here it is the expression for the loss of head due to the friction in a pipe. Loss of head due to the friction in the pipe. You can see that over here the pipe, which is the circular in the cross section and having two limits, section 1 and section 2 over there is a pressure P1 which is applied to the flow direction and the pressure P2 that is applied in the opposite to the flow direction. So the P1, that is the intensity of pressure at a section 1 likewise the velocity at the section 1 that is denoted by V1, L that is the length of pipe between the 1 and 2 D that is the diameter of pipe, F dash that is frictional resistance per unit weighted area per unit velocity. You need to remember this term F dash, small f dash, that is the frictional resistance. Okay, F dash that is frictional resistance per unit weighted area per unit velocity. HF, that is the loss of head due to friction. In the previous session there was again HF, that is the drop of pressure due to the head, and that was the 32 mu U bar L okay, divided by rho GD. That was about the flow of viscous fluid between parallel plates and the flow of viscous fluid through the circular pipe. So here in this case we are having one circular pipe and we are going to find out the loss of head due to the friction in this pipe, and the P2, V2, that are the values of pressure intensity and the velocity at a section 2. So we are having one this pipe and all of this pipe, these are the basic nomenclature for this pipe. Okay, now let us applying the Bernoulli's equation between the 1 and 2 section, and the total head at a 1 that equals to total head at a 2 at a section 2 plus loss of head due to the section between the friction between the 1 and 2. So total head at this section 1 that will be equals to total head at a section 2 plus loss of head due to the friction between this 1 and 2. So this one is our Bernoulli's equation. You can see that the Bernoulli's equation we had studied in our previous chapters, that is the P1 by rho g, that is the pressure head, plus V1 square by 2g. So P1 that is your pressure energy, second one that is kinetic energy, and third one that is your potential energy, that is Z1, that equals to P2 upon rho g plus V2 square by 2g plus Z2 plus head loss due to friction between the section 1 and section 2. So here it is the Bernoulli's equation which is applying at the section 1 and 2. But as we all know that this is the horizontal pipe, so that the potential head, that is Z1 equals to Z2, so it will be directly cancel out, plus V1 and V2 as a diameter of pipe is the same as 1 and 2. So that will be again same V1 and V2. So we can write that P1 by rho g that equals to P2 by rho g plus HF. So the HF, that is head loss due to friction, that equals to P1 divided by rho g minus P2 divided by rho g. So here it is the HF is head loss due to friction. That's why the intensity of pressure will be reduced in the direction of flow by the frictional resistance. As we know that the higher the pressure at the section 1 1 and lower the pressure at a section 2 2. So we can say that the intensity of pressure that will be reduced in the direction of flow whenever you are going throughout the length of pipe. So now let's say the frictional resistance, that is the F frictional resistance, that equals to frictional resistance per unit weighted area per unit weighted velocity, that is F dash into weighted area into velocity square, that is your frictional resistance F. Okay, so here it is F1, that is frictional resistance, and F dash, that is frictional resistance per unit weighted area, and per unit velocity, that is F dash into weighted area. Weighted area, that is the perimeter of this circular pipe, that is pi dl into V square. So in this case pi d, that is the perimeter, so this pi d that is replaced by P, and the remaining term, that is L, which is put it over here, L into V square. So here it is the F1. So, and the force that is acting in this pipe, that is the first one, pressure force at a section 1 1, that is P1 into A that is the area of pipe. Likewise, second pressure force, that is P2 into A again, that is the area of pipe. And third one, that is frictional force F1, that is frictional force F1. Now resolving these horizontal forces in the horizontal direction, so we can write that in the flow direction, that is P1 into A, opposite to the flow direction, that is negative of P2 into A, and the opposite of the flow direction, that is frictional force F1, that equals to 0. So here it is the resolution of the forces in horizontal direction. So this A is take out as a common outside to the bracket, so P1 minus P2 into A, we can write that P1 minus P2 into A equals to F1. But the F1 is frictional resistance, and it is already find out like this, that is the F dash into P into L into V square. So we can write that F dash P into L into V square in the place of F1. So here it is the P1 minus P2, this A is divided by this whole term, so we can write that like this. But we know that the P1 minus P2, that is the drop of pressure, we can write that like this, P1 minus P2, that is rho G HF. By putting the value of P1 minus P2 is rho G HF, and over here that is F dash P into L into V square divided by A. So HF, that is head loss due to friction, that equals to F dash divided by rho G. This rho G is going towards over here, P divided by A into L into V square. So we can write that this equation like this. P upon A, which is weighted perimeter divided by area. So weighted perimeter, that is pi d, and the area of circular pipe, that is pi by 4 d square. So P upon A is 4 divided by d. This P upon A is, we can write that 4 divided by d. So let us put the value of P upon A as 4 divided by d, and the remaining terms are the same. So F dash rho G into 4 FLV square divided by D. So here it is the HF, that is F dash by rho G 4 FLV square by D. By putting the value of F by 2 by F dash by rho, as F is known as the coefficient of friction. F, that is coefficient of friction. F dash, that is the frictional resistance. So let us put the value 4 FLV square by 2 GD. You can write that over here, 4 FLV square by 2 GD. So this equation is known as the Darcy-Weber equation. And you need to remember this equation HF, that equals to Darcy-Weber equation, that is 4 FLV square by 2 GD, that is used to finding out the loss of head due to the friction in a pipe. So the HF equals to 4 FLV square or FLV square by 2 GD, where the F is known as friction factor. Okay. So thank you. That was all about our today's session. So you need to write out this whole derivation by yourself and submit it to the Google Classroom. So remember one thing, this is the most important topic of this whole unit. So please remember this unit, write down by yourself and submit it to a Google Classroom. Thank you.